Hi, I'm going to continue on doing problems from Stewart. We're on number 11. Okay, so we've got this integral, and here's where we start getting into the games that people play. This is such a contrived integral, it's so rigged, but it looks confusing. Now, one of the things you got to at least have a kind of a checklist. What are you good at? Well, just looking here, we've got a square root, we've got this x plus 1. Are we good at the square root of u du? Can we do that? If we could, then maybe picking u to be the stuff inside the square root would be a good idea. But if you kind of look ahead, you might think, oh, how's that going to help? Because I've got this x plus 1, but let's just try it. Okay, so it's just good advice when you're new at this and you're just trying things. Pick this stuff inside the square root. Pick the whole thing inside the square root. It's not always true, but for right now, it's probably a good choice. Okay, 2x plus x squared, and then we always take the derivative immediately. So we get 2 plus 2x times dx, and it's really 2 dx plus 2 dx from this and 2x dx from that. So it's really parentheses, and you got to have that there because otherwise it's going to be hard to substitute. You have a little setback here. Okay, so you got to have the whole group times dx, or factor it out after you put them on each one. Okay, now our goal is to take this integral and convert it into u. And we have the square root of u because I chose u to be the stuff inside the square root. But I still have the x plus 1 dx to account for. And it usually comes from this area, but I don't see it right away. But if you squint, you'll see that this here is the same as 2 times 1 plus x dx. So there's my 1 plus, 1 plus, and look how they chose to switch the order to confuse the enemy even more, right? It's x plus 1 here, but then they put it in this order so that you get 1 plus x, right? It's just a little bit of a, but they're the same thing. Okay, so this 1 plus x dx is equal to du, so 1 plus x dx is equal to 1/2 du. So the stuff I need to substitute for is equal to 1/2 du, and it looks like we're home free. This is a good integral to have memorized because you have to deal with the fractions. It's really square root of u is u to the 1/2. So I'm going to add 1. That's like adding 2 over 2 to get u to the 3/2. And then I have to divide by that very 3/2, but that's the same as multiplying by 2/3. And so that's what I'm saying is that a good idea to just memorize square root of u or square root of something is u to the 3/2 times 2/3. All right, but I have that extra 1/2 out in front, so our final answer, or close to our final answer, is 1/3 u to the 3/2 plus c. And now I have to put it back the way we found it. We said that u was 2x plus x squared, so my answer is 2x plus x squared to the 3/2. That's our answer. So see why I said it's just to confuse the enemy problem. Look at what they did. Let's just take a second here to create one ourselves. Let's say I wanted to create an integral that ended up being something like root u du, maybe it has a constant in front. Well, I'll just create some nonsense, right? I'll just put, ln x plus e to the x on the inside. And then if I'm going to make this a u substitution that works, I better have the derivative of whatever's on the inside on the outside so that I can make the u substitution. And then when I do the du and solve for the remaining stuff, I can make the substitution. So I would have 1 over x plus ex out here. And you see, that's how we build these integrals. That integral will convert perfectly into square root of u. Okay, so That's a good way to do it, to learn integrals, is to build them yourself. And I'll do a little bit of that with you. Once you start building them yourself, then you look at them and you say, oh, geez, I see how that's made. Okay, let's keep going. Number 12. Okay, it's our old friend secant squared. And now we've got 2 theta. Thetas are variable. And the design of this is to remind you that the thing whose derivative is secant squared is tangent. Okay, so the integral that you're supposed to have in your repertoire is secant squared u du, and that's equal to tangent of u plus c. This is the one you're supposed to have in your mind, so when you see secant squared, you immediately say, oh, gee, I'd love for this part right here to be u, and then I can do it, so let's see if we can get that done. U equals 2 theta, du equals 2 d theta, and this substitution goes as follows. We have secant squared of u because we said u was 2 theta, and then the d theta part that I have left to substitute for, that's equal to 1/2 du. So I put the 1/2 out here, I've got the du, and I've got the integral that I'm a world expert at. I get tangent u, plus c, and then we have to put things back the way we found them. Tangent of 2 theta plus c. You can take the derivative of that and see if you get back to what we started with. Number 13. Okay, number 13. In the book, it's colored red, and they have some explanation for that. I forget what it is, but I always think these are kind of classic test questions. It's not just not totally simple, but it's also designed to remind you of a specific thing, that's kind of standard to know in calculus. Okay, and so here's a new integral. We haven't seen this one. The integral that you're supposed to have in mind and that you're a world expert at is this integral, the integral of 1 over u du. And the thing whose derivative is 1 over u du is ln, absolute value of u. Okay, so if I want to get 1 over u, well, I better pick the bottom part to be u. So u is 5 minus 3x, and then du is negative 3 dx. Okay, so I'm going to substitute for everything I see here. On the bottom, I just have u, and then the dx, that gives, I solve for that, and I get dx is negative 1/3 du, so I put the negative 1/3 out front. I have du on top, and you can write it this way, or this is negative 1/3, 1 over u du. That'll maybe prompt the ln answer maybe better than having it written like this, but you have to get used to these different ways of writing things because you can't control how somebody else presents it. Anyway, this gives you a negative 1/3 ln. I don't think the Apple Pen likes the way I write ln. Ln of u, and then I have to put things back the way I found them. And I get u is 5 minus 3x. Any questions? Just kidding. I know there's nobody watching my stream, but that's okay. We're just getting started here. Okay, number 14. Integral of u. Oh, here's where you see it's funny. I gotta laugh at some of these. I know kind of what the authors think. So here we go. It's like here we're supposed to use substitution, but they present it in u. So what are you going to do? How are you going to do a u substitution? But again, okay, putting that aside, if you if you need to, if it makes you feel more comfortable, by all means, just switch it to X to get the job done. Okay, but the design is to kind of let you grow out of your security blanket of everything being in X and then everything being converted to U. So here we're going to do a V substitution. What a revolutionary idea. I have to use some other variable because U is taken. Anyway, this is our old friend square root. Pick the stuff inside the square root as your first chance, right? Because we do know how to do square root of U du. Okay, that's going to be, as I discussed, it'd be great if you could just have that memorized. You don't have to reinvent it every single time. Okay, so that's the one we know. I'm going to do V equals 1 minus U squared. And then when I do the conversion here, I get the integral of, well, square root of V, and then I still have to substitute for the U du. See, that's not done yet. I forgot to get dV here. Let's go, getting ahead of myself here. I'm so excited. Let's do our dV, which is what we're required to do. Okay, so as soon as I pick the V, I'm going to go dV, and I get minus 2U du. And then we do our conversion. I get square root of V, and I still have to substitute for the U du. So from here, I get U du is negative 1/2 dV. And if you're advanced and you don't really want to write this out, of course you won't, but you don't have to. I'm just writing it out for the purpose of the video, but a lot of times people just do this part in their head. They just see what the U du is. Okay, anyway, U du is equal to negative 1/2 dV. I'll put the dV here, negative 1/2, and that gives me negative 1/2 times 2/3 V to the 3/2 plus C, which is negative 1/3 V to the 3/2 plus C, and then I got to put things back the way I found them. V is equal to 1 minus U squared. And there's our answer. We got such a pile of integrals here. This one's just to get you thinking about trig functions. It's a simple one, but if it's this is a good litmus test. If this is a hard integral for you, then you need to do it maybe several times in a row. It's a good idea to just keep doing the same one because it'll start to click so if all you can do is kind of copy it, then get as far as you can without copying, then look and then try again and see if you can get all the way to the end without looking. And that's how you kind of build up your integral chops. Okay, so the design here is that everybody's supposed to be a world expert at this. So the thing whose derivative is sine u, in other words, the antiderivative, well, if I take the derivative of cosine, I get negative sine. So the antiderivative of sine must be negative cosine. And so since that's the one I'm a world expert at, then I can pick u to be pi t. Then du is pi dt. When I go to substitute for everything I see here, I get sine of u by design. The only thing I have left to substitute for is the dt. So from here I get dt is 1 over pi du. Okay, let's put that in, 1 over pi du. And that's another one too, right? It's a little bit uncomfortable to look at that pi there instead of, say, 3 or a 7. Pi is a letter, a Greek letter, right? And so you got to process that. That's how they kind of turn up the math stove. It's still at simmer, though, just a little bit more. Okay, anyway, let's finish this up. So we get 1 over pi times negative cosine u plus a constant. And then I can clean that up with the negative there. I get cosine, and then what was u? U was equal to pi t. And there we go. And again, I just said it, but I think it's worth repeating. Take these integrals. I've done them for you. Do them yourself and just see if you can get all the way to the end without looking at what I've done. And if you get stuck, it's okay. Look at what the next step is. Say, oh, okay, that's right. But then go back to the beginning and do it all the way yourself. You don't just start where you got stuck and continue. If you want to learn the whole process, be willing to do the work and actually go from the beginning to the end. That's going to help your brain out to process this stuff. Number 16, sticking with the trig theme, but now we're incorporating e to the x. Now, when we started this chapter, e to the x was one of the first ones, and e to the u du is one of the easiest integrals to do. So you'd like it to be that, but thinking of it as e to the u here is not going to help you because how are you going to get the cosine involved? But what we do know is this integral, cosine of u du. That's equal to sine u. All right, so that's the one we know, and so the way to get towards that is if I let u equal e to the x, then at least I'll have cosine u. Let's see what else we get. Du is e to the x dx. When I convert this integral, I get cosine of u by design. And the thing I have left to substitute for is e to the x dx. Well, look at this. I've got it. E to the x dx is du. I don't even have to do an extra step. So I have cosine u. And then the antiderivative of cosine is sine. But the problem was given to us in x. So I have to replace the u with e to the x. We'll put the parentheses around there. Number 17. E to the u over 1 minus e to the u. E to the u over 1 minus e to the u squared du. It's that trick. It's that confusing enemy trick where they use u as the variable. So now we got to use v. That's okay. You can use t or something, or you could use x, whatever you like. I'm going to use v. So here I'm looking at that and I'm saying, geez, that's awfully complicated. But do you notice how you have this parentheses with an exponent? And if I can just, that's really a -2 exponent if I take it out of the denominator. And I know that I can do things like the integral of v to the -2 dv, because I can do anything with an exponent. The -1 exponent is a special case, but all the other ones are fine. So let's try that. Let's pick v equal to 1 minus e to the u. Not 1 minus e to the u squared, just the stuff on the inside of the parentheses. Then dv is negative e to the u du. This integral converts into 1 over v squared. And then what do I have left to account for? I have left the e to the u du. I've accounted for this part, but not the e to the u du. And look at that. I've got it right here. E to the u du is minus dv. So we'll put dv here, put a minus out in front, and we're good to go. This is the same as negative the integral of v to the -2 dv. And now we can go to work on our exponents. So I'm going to add 1, which will give me -1. So in order to keep track of all the constants and stuff, I like to just leave the negative out here and then put a little box and do my integration, and then I can do a little housekeeping afterwards. So I'm going to get v to the -1 over -1 plus c. And then the housekeeping, the negatives cancel. I just get v to the -1, which is really 1 over v plus c. And, oh, nope, I don't want to put a box around that. See, if I had people here, you might catch that for me. So let's take away my box. Okay, we got to put things back the way we found them. So it's 1 over, what was v? V was 1 minus e to the u. So I have 1 minus e to the u plus c. There we go. Now it's done. I don't think you really need parentheses. Number 18. Sine of root x over root x. So here's something that helps for integration. It helps in integration to know that the square root, the derivative of square root of x is 1 over 2 root x. That way you don't have to reinvent it every time. The square roots are good to know, both derivatives and the integrals of 1 over root x and root x. In this case, see, the thing that I'm really good at is integral of sine u. And I see the sine and I say, oh, that'd be great if I could get sine u, but then I see that other root x and I have a little doubt in my mind that that might work. But when you remember that the derivative of root x is equal to 1 over 2 root x, then you see, well, sure, there should be a denominator with a root x in there. Otherwise, I wouldn't be able to do the problem. So rigged. Okay, let's try it. So u equals root x, and then du is 1 over 2 root x dx. When I convert this integral, I get I get sine of u by design. What I have left to account for is this dx over root x. But look, I've got it right here. Dx over root x is equal to 2 du. Okay, so I'll put that in now. I've got a 2, and I've got a du, and there's my integral that I'm a world expert at. The antiderivative of sine is negative cosine. Remember, the derivative of cosine is negative sine, so I have that little extra goodie in there. The negative, let's do it the way I just said last problem. So I'll have the 2, and then inside the box I do the integration. So I get negative cosine of u plus c, and then we can do a little housekeeping. Negative 2 cosine, and then u was root x, so I'll put the root x in, plus c. Go ahead and take the derivative of that and make sure we get back to the original. Number 19. Oh boy, these are getting kind of sassy here. We got a plus bx squared over square root of 3a plus bx cubed. Yes, dx. Well, would you look at that? Now, doesn't that just make your brain shut off? But you can't, okay? So you got to say, what do I know how to do? I see that square root, and I say, well, at least I could do this. I feel like I can. And by the way, what is that? Let's just do it real quick so we have it ready. That's the same as the integral of u to the negative 1/2. And then when I add 1, I get positive. Remember, I'm adding 1, so I add 2 over 2, so I get 1 over 2, which gives me u to the 1/2, divided by that very 1/2, which is the same as 2u to the 1/2, which is the same as 2 root u. And I hope you can appreciate that you don't want to do that every time. So let's remember that the integral of 1 over square root of u is 2 root u plus c. That's a good thing to remember. I may not use that when I'm doing it. I might still work it out every time, but I recommend that you add this to your repertoire, add this to your memorized integrals. The way you have 1 over x, that way it's absolute value x. All right, so I kind of spilled the beans here. I'd love to have that 1 over square root of u, so let's do that. U equals 3a plus bx cubed. I'm not really seeing it here, but let's just keep going. You look around, you go, yeah, is this really going to work? But sometimes you just have to follow your nose. Okay, so I'll take my derivative, as I always do, after I pick the u. I get, here, this is all in x, right? So this was an x here, actually. I think I cut. Oh, there's the x. The x is, yes, there's the x. There we go. Okay, so the derivative of 3ax plus bx cubed is 3a plus 3bx squared all times dx. You had 3a dx and you had 3bx squared dx, but then just factor it out and have it on the outside. All right, let's start to convert our integral. I was hoping it was going to be square root of u on the bottom there, but I still have to account for this a plus bx squared dx. But look here, this is the same as 3 times a plus bx squared dx. Wow. And so since that equals du, we have a plus bx squared dx is equal to 1/3 du. I can put that over here. 1/3. And we just did this integral, so it's 1/3 times 2 root u plus c. I don't know why my hand wrote a 2, because I was looking at it, I guess. And now let's put it back the way we found it. We had u was equal to 3ax plus bx cubed. So I get 2/3 square root of 3ax plus bx cubed plus c. Number 19, that is number 19. Let's do number 20. 20. Z squared over z cubed plus 1 dz. Okay, a lot of gobbledygook there. We got a fraction. We don't have a parentheses and an exponent. We like to see that, right? Because then we just pick u to be the stuff inside the parentheses. But remember, there's a hidden parentheses on the whole denominator, and one of the integrals that we're supposed to be world experts at is 1 over u du. That's ln absolute u plus c. Okay, so if I can get that going, I'm good. So I'm going to pick u equal to z cubed. Now what I do, I'm looking ahead. As soon as I pick my u, I know I'm going to take the derivative, and I'm scouting around to see if I see a z squared somewhere, because I know I'm going to need one from this z cubed. But you see how rigged it is? The z squared is there. So we just keep going. I'm getting all giddy because we know it's going to work. 3z squared dz. Remember, the derivative of 1 is 0. And now when I convert this integral, I have 1 over u. And what I haven't accounted for yet is the z squared. I wrote dx. Well, see, sometimes following it. Okay, anyway, so I haven't accounted for the z squared dz. And look at that, it's right there. So I have z squared dz is 1/3 du. Let's put the 1/3 there, du. I'm good at this integral. And that's equal to 1/3 ln absolute value, z cubed plus 1. Okay, what number was that? That was 20. Okay, number 21. Let's keep going. Oh, yes, another red problem. This is red. Guess I'll start doing that. Okay. Well, you see that parentheses in that exponent? It'd be great if you just picked u to be the thing in the parentheses, because then you'd have u squared. But would you be able to account for everything else? And the answer is yes, because look ahead. If you pick u to be ln x, what's the derivative of ln x? Well, it's 1 over x. And we have that there. 1 over x dx. Okay, when I go to convert this integral into u's, I get u squared, because u is ln x. And then I still have to account for this, but I have it. Dx over x is du. So that's u cubed over 3. And then we can put back the u that came in the problem that I assigned. There we go. It's done. And I want to dwell on this a little bit because you see how this is kind of this is, in my opinion, this is why they made it red in the book, because this represents a standard kind of problem on tests and also, in test prep books and things like that. It's when you have ln of anything, you got to have a 1 over x in the integral, otherwise you can't do it, right? So, and we'll learn other techniques to do ln, but at this stage, I have to have a 1 over x. So, if I want to have square root of ln x in the problem, I better have a 1 over x. If I want to have sine of ln x, I better have a 1 over x. Otherwise, I'm not going to be able to pick u equal to ln x. You see, the 1 over x has to be in the problem in order for it to be done when you have this ln x inside of some other function. And then so you see how rigged it is, right? You can keep going with this, but anything that even in the denominator, right? If I have square root of ln x in the denominator, well, I better have a 1 over x down there with it. Otherwise, you're not going to be able to pick u to be ln x. Okay, if you didn't understand what I was talking about there, that's okay, let it go. When you're a beginner, that might be too much for you, but those of you who've been doing this, that was maybe helpful. Integral of cosine to the 4th theta sine to the sine theta. And again, this is so rigged because the derivative of cosine is minus sine. So if I take this here and make it u to the 4th, well, I've got the du here. Almost, there's a minus, but you see how you can kind of look ahead and know that your choice of u is correct. But in general, remember cosine to the 4th theta, that's the same. This is just notation. That's the same as cosine theta to the 4th. We just don't write it this way. But this is a situation where you have a parentheses to an exponent, and it's good advice often to leave the stuff inside the parentheses. So I'll pick u, not cosine to the 4th. U equals cosine theta. So then du is minus sine theta, d theta. Let's account for everything we see in our integral here. The cosine to the 4th is going to become u to the 4th. And I still have the sine theta d theta. Well, I get that from here. Sine theta d theta is equal to minus du. Get the du here, put a minus out in front. This equals u to the 5th over 5 plus constant. And then do a little housekeeping. We have a minus. What was u? U was cosine. So we have minus 1/5 cosine of cosine to the 5th theta. Now see if you could just do this in your head, because couldn't you see, some of you, look ahead and see, this is u to the 4th with a minus. So it's u to the 5th over 5, and so it's cosine to the 5th over 5. As long as you have the sine coming along for the ride, you can do cosine of any power. It's root cosine sine, right? I have a 1 over cosine to the 7th, but gotta have a sine there, otherwise I can't pick u equal to cosine. You see? So once you can do this one and you see how it works, then any power of cosine works as long as you have a sine right next to it. And if you don't, well, that's another section of the book, and we'll see how to handle that. But for right now, if you have a big pile of sines, you got to have one cosine, and if you have a big pile of cosines, you got to have one sine. Otherwise, the u substitution doesn't work. (23) It's the same concept for this one. You see how this is the derivative of tangent. So if I pick u to be tangent, I'm going to get u cubed du. And then that's u to the 4th over 4, and so that's tangent to the 4th over 4, plus c. But let's write that out loud. So we picked u to be tangent, but the reason I think of that is because I see the secant squared. So if u is tangent, then du is secant squared theta d theta. And I have to substitute for everything I see here. I get u cubed for the tangent part. And then the secant squared d theta, well, it's right there. It's equal to du. But once you've done a lot of these, you can kind of see that ahead of time. And you don't even have to write out the substitution. You can say tangent to the fourth over 4. And if you never want to do one in your head, that's fine too. I'm just offering that as a possibility for those who want to tie their brain in a pretzel sometimes. Okay, there you go. I think we'll make this one the last one. 24. 24. We got a little confuse the enemy going here. We got root sine of 1 plus x to the 3 halves dx. Now, after you get over your deer in the headlights moment, you say to yourself, geez, I'd love it for it just to be sine u. I mean, that'd be great. That would make my day. Okay? And if it was going to be sine u, well, then this part here, all this stuff inside there, that has to be u. But look ahead. If I take the derivative of x to the 3 halves, don't I get x to the 1 half with a little constant in front? But x to the 1 half is just square root of x. So it's really going to work out. Let's try it. U equals 1 plus, and if you're new, you're not going to see all that. You're not going to be able to follow along with what I just said there because I've done a lot of integrals, and some of the people watching the videos may have also, so that's why I say that. But if you're new at this, you just pick the stuff inside the parentheses and follow your nose. Pray. What's the first step? Du is, well, derivative of 0, derivative of 1 is 0. Derivative of x to the 3 halves is 3 halves x to the 1 half, because I'm subtracting 1, which is the same as subtracting 2 over 2 dx. And I'm going to even take an extra step to remind myself that that's 3 halves root x dx. Now let's convert this integral. I have sine of u by design. And what I have left over is the root x dx to account for. So root x dx is equal to 2/3 du. I wrote that wrong over here. So let's fix it. Okay, so I was accounting for the root x dx, and it is 2/3 du, so I put my 2/3 out here, and I put my du, so I get 2/3. Remember, it's minus cosine u plus c, which is negative 2/3 cosine, and what was u? It was that monstrosity 1 plus x to the 3 halves. Now, another way to even disguise this further and really maybe confuse the enemy more is to rewrite it like this. Root x sine of 1 plus x root x. How about that? Because that's the same. This is the same as x to the 3 halves. This is Robert. This is Bob. Same guy. Okay. Well, that's enough. Okay, that's I've done the first page of that up to number 24, and geez, it only goes up to 92. It's got just integrals alone will be up to number 72. So there's a lot of work left to do. I'm just getting started on my student. Okay, thanks for watching.